In this video, we'll explore how to install Rook on Kubernetes to manage your own cloud-native storage. Rook is essentially a layer built on top of Ceph, a robust open-source storage system that provides redundant, distributed storage for cloud environments and even bare metal servers. What makes Rook special is that it brings file, block, and object storage capabilities directly to your Kubernetes clusters in a truly cloud-native way. We'll be deploying Rook on Google Kubernetes Engine, but don't worry if you're using a different platform. Whether you're on Amazon Web Services, Microsoft Azure, your own bare metal setup, or something else entirely, the principles we'll cover apply broadly. Rook is a mature open source project with extensive documentation, active community support, and full access to the source code if you need to dive deeper. There are actually several approaches to installing Rook, but we'll focus on the most production-ready method, which is using Helm. The Helm chart will deploy the Rook operator, which is a powerful controller that understands custom Kubernetes resources. These custom resource definitions, or CRDs for short, allow us to define and manage our storage infrastructure using native Kubernetes commands. The operator installation only takes a couple of commands, and once it's running, deploying our Ceph storage will be equally straightforward. If some of these concepts sound abstract or confusing, that's completely normal. We'll demystify everything as we go through the process together, step by step. Let's get started. Navigate to your Google Cloud project and head to the Kubernetes engine page. Here, we'll create a new cluster. This is a critical point to remember. You must select a standard cluster, not autopilot. The standard cluster gives us the low-level control necessary for managing storage properly. To save a bit on costs, we'll choose a zonal compute class, but aside from that, the default settings should work well for our needs. With our cluster spinning up, we need an integrated development environment or shell to handle our Helm deployment and create our custom resources. For convenience, I'm using Google Cloud Shell with its built-in editor. This is a turnkey, browser-based solution that requires minimal setup and is completely free. Of course, feel free to use whatever environment you prefer. Now let's talk about the actual installation. First, we need to add the Helm repository for Rook. Remember, you'll need kubectl properly authenticated to your cluster and Helm installed locally or in your shell environment. If you're following along on a different platform, consult the Rook documentation for platform-specific authentication details. Before we can run the authentication step, Gcloud is prompting us to set a Google Cloud project value. That's no problem, we'll handle that quickly. Once we're authenticated, we can run our Helm installation command. If you have specific configuration needs, you can pass a values file using the -f flag. The default values are well documented and available in the official Rook Git repository. Look under the Deploy Charts Rook Ceph Values YAML path to explore all the customization options. There are many things you could tweak, but for now, we'll opt for a pretty basic installation to keep things simple. The Helm installation completes successfully, but there's an important reminder. We still need to actually create resources. This is true. If we check the pods in our newly created namespace from that Helm installation, we'll see the Rook operator and a CSI controller manager. These are essentially management workloads, the brains of the operation, that allow the custom resource definition storage instantiation to actually work. They don't provide storage on their own. Next up is configuring our Ceph cluster. The deployment examples in the Rook documentation offer several excellent templates as starting point. Since we're running on Kubernetes and not really on bare metal, we'll use the cluster on PVC type installation. Note that for bare metal deployments, you could use the cluster YAML file instead. I'll grab that configuration file and point it to our namespace. Before creating the Ceph cluster, let's address an important consideration: priority classes and resource quotas. Priority classes are a standard Kubernetes construct that help ensure critical pods don't get evicted at the worst possible moment. Nobody wants that. We need to make sure our new Rook Ceph namespace has proper resource quotas set up. This guarantees that our critical storage pods have the necessary resources and aren't preempted by other workloads. We'll apply a resource quota so those key pods always get their slice of the pie. With the resource quotas in place, we can now apply our cluster configuration and try to create our cluster. We'll see various pods spinning up, including a detect version job and monitor pods, among other things. It's important to keep an eye on these to make sure everything progresses cleanly. A clean startup now saves debugging headaches later. As these resources start spinning up, we're beginning to encounter some issues. We have both some errors appearing and some pods that seem to be stuck in pending status. Let's investigate why these are getting stuck. It looks like the problem is due to CPU pressure on our nodes. Our nodes don't have enough CPU resources available. We might want to expand our node pool a little bit. Let's go to our cluster and offer a bit more room by expanding this E2 medium node pool, which gives us just about 3/4 of a CPU per node. We'll expand that to, let's say, 4 or 5 nodes. Hopefully that will clear up that resource constraint and give us more breathing room. We should also check on this crash looping pod for the node plugin. Looking at the logs, it appears the pod wants the RBD kernel module to be available on the host path of the actual nodes. We may need to work with that in just a little bit, but let's see if these other containers can spin up in the meantime. Unfortunately, it looks like we're still having some struggles with scheduling. Again, it's not liking the available CPU, it would seem. So we have another option. We can actually just create a larger node pool altogether. Instead of these E2 medium nodes, let's create a user-managed node pool. We'll keep it at 3 nodes, but use much larger machines. We'll also use Ubuntu as the operating system because that's going to be easier for doing low-level installation work. We've got general-purpose E2 instance types available, so let's bump this up quite a bit to maybe E2 standard 4, for example. I think that'll probably be all right. Let's create that node pool. As that node pool is provisioning with our bigger machine, we can probably delete the default node pool and get all those workloads to migrate over to the new, more powerful nodes automatically. Why pay for 2 pools when we only need 1? Once that node pool switch over to our bigger machines is all set, let's pop into our Cloud Shell here. I like this situation a lot better. We've got lots of different pods running now. Notice that when you see 3 different replicas or 3 different pods for one workload, that probably means it's a daemon set, so it's running 1 pod per node across all 3 nodes. However, we still have this one pod here that seems to be a little bit stuck. Let's check that out and see what's going on. Looking more closely, it appears that these monitor pods, which are important components, have some persistent volume claims that aren't being fulfilled. Let's investigate further. Indeed, it looks like that's the case. We have this GP2 CSI storage class being referenced, but I don't think that's actually available in our cluster. That storage class might be AWS focused. Let's see what we do have available here in our GKE cluster. All right, so we have a few different types of persistent disk storage classes available. Let's use just the standard storage class instead. We'll change that in all instantiations of this cluster configuration. Let's apply that new cluster YAML file, which will hopefully update our stateful set and persistent volume claims. Now, unlike something like Helm, where deployments are super instantaneous when you run new deployments, these CRDs are reconciled by the operator, and that can sometimes actually take a little bit of time. So be patient if these things, like for example our storage class here, doesn't change immediately. It should hopefully change shortly though. The operator needs time to percolate through the changes. If we sit here for a while and things aren't changing, it might be worth checking a few things. First, we can check the pods, and specifically the operator pod, which doesn't always seem to be doing anything visible, but may actually be working behind the scenes. We can also, of course, check the pods that are failing to spin up that are intended for these persistent volumes. Since the operator pod looks fine and is running normally, we might just need to give the system a little kick. We could try removing those PVCs or possibly just recreating the cluster altogether. Not the Kubernetes cluster, mind you, but rather just the Ceph cluster itself. And just like that, we have some great looking PVCs. Admittedly, these are pretty small PVCs, but they were successfully provisioned, and that proves the pipeline works. Now, hopefully, we've got everything we want running in the Rook Ceph namespace. Indeed, it looks like our monitors are coming up now, spinning as expected. I believe we'll have 3 monitors total because we specified that in our configuration, so we just need to wait for 3 of those to spin up and report ready. As you can see with this huge list of pods here, we get a ton of stuff that's running when we set up this Ceph cluster. That's sort of the power of Rook. It orchestrates all this pretty complex storage work that involves lots of different components, and it does that for us automatically on our Kubernetes cluster. No manual YAML marathon required. It looks like we have just a little bit left that's pending. We'll give the pods a minute or two to make sure everything is fully stable and it's not going to spin up anything else. Now, I'd say that looks pretty good to me. Everything now shows great. Let's also just get our Ceph cluster custom resource and check its status. It says that everything was created successfully and we have OK health status or health OK, which is exactly what we want to see. So now for the fun part. Once our cluster is cleanly up and running, we can create object stores. This gives us S3 type storage capabilities, and in fact, the object storage is specifically S3 API compatible, which is pretty cool. This means it behaves just like Amazon Web Services S3. What we're doing here with this CephObjectStore resource is specifying a number of underlying storage parameters. Then we define this gateway here because S3, or object storage in general, is basically consumed through an API, so we need a gateway like that to provide access. After the Ceph object store here is created, the Rook operator will then create all the pools, secrets, services, and other resources necessary to start the service automatically. Again, we can look for pods here, and we're specifically looking for the Object Gateway pods, or RGW pods, which serve the S3 API. Honestly, I'm not totally sure if our single pod is all that we expect here. Let's go ahead and check our CephObjectStore resource to see if it looks ready to go. Indeed, it looks ready to me. We even have this nice endpoint here. You can see that this is an internal type service. There's our demo store, so this has an internal cluster IP address. This internal IP here is basically how we're going to consume that object storage. As a next step, we need to create a bucket. So we'll create a new file for that. It's going to look like this. Basically, this is going to be a storage class. Let's call this maybe demo bucket, for example. When we have our namespace and then this provisioner that shows we're going to be provisioning the storage when it's requested through the Ceph system using the Rook Ceph provisioner. Just make sure, of course, that you have the object store name and the namespace correct in this storage class. Double check those details. You can see that up here, we've got the storage class that was created a few seconds ago using that Ceph Rook provisioner. A quick kubectl get storage class confirms demo bucket was created successfully. Now we'll complement this bucket resource with a bucket claim resource. These don't necessarily have to be one-to-one, but we're going to go ahead and opt for that simplicity. So we'll call this our demo bucket claim, and we'll use that demo bucket storage class name from before. We should probably have this in our Rook Ceph namespace as well, so let's make sure we specify that and place it in the Rook Ceph namespace. We can see that this is bound. kubectl shows the claim is bound with no errors or events, which could potentially be a good sign. Ready for the ultimate test? Let's push and pull a file via S3 to prove this actually works. For the ultimate test here, let's use an S3 API compatible client library and see if we can basically put and get a file from our brand new storage. We're going to download the S5CMD command line tool to do that. This is a quick smoke test utility that allows us to interact with S3 compatible storage. For our access, remember that we have the actual endpoint running on our cluster. So if we get our services in the Rook Ceph namespace, you'll see this is kind of what we want to target here. This is the ObjectStore Gateway service. What we're going to do is we're going to do a port forward to that service on port 80. This would basically mean that our local IDE here will be able to access that service through localhost. Let's give this a try with a test file. For this S5CMD, we need a few things. First, we need our endpoint URL, which is going to be just localhost, and we're going to copy that test.txt file to our S3 bucket, which again we named demo bucket. Our S5CMD attempt fails with the 404 error. It looks like we'll actually need credentials here to authenticate with our storage. So I'm going to bring in a way that we can basically read a config map and a secret that contains some of our credentials and connection details for our demo bucket. All we need to do is basically get certain parameters from that config map and from the secret. Note that we have our config map in this Rook Ceph namespace rather than the default one. Just to show you the idea here of what we have, we've got a config map which contains some connection parameters, and then we also have a secret which contains our actual access key ID and secret access key. Let's set all of these things together and just run these commands real quick to make sure this all works well. We can read these into environment variables. And let's retry that s5cmd command. Alright, since we're still getting the 404 error, I wonder if we just don't have our credentials configured properly. Let's run a couple of quick commands. What we're going to do here is set up an AWS credentials file, which includes our access key ID and secret access key that we just saved to our environment variables. I'm going to show you these here. We have our secret access key and our access key ID. Remember, we pulled them from that secret in our Rook Ceph namespace. Let's see if that happens to fix things. And no luck there. Still getting the 404. Now, as a little debugging step, we can use normal S3 type commands. Let's do an ls to list what's actually there. Okay, and it looks like it actually put this UUID type suffix on the end of our bucket during provisioning. So let's update our bucket name now to include that full name with the UUID suffix. And look at that, success. We've got our object storage all set. We're moving a file to it, and then when we download that file, we'll see that it contains the same content as earlier. This confirms our Rook Ceph object storage is fully functional and working exactly as expected. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include all code and the diagram file in the description as well. If you have any questions, please post them in the comments section and we'll do our best to respond. Thank you very much for watching till the end, and please enjoy responsibly.